Hello and welcome to the presentation of the paper In-Time 3D Reconstruction and Instance Segmentation from Monocular Sensor Data. My name is Stefan Schurischuster. We are in the field of augmented reality and we are tackling two problems with our work. First is occlusion. So we want to have real-world objects occluding virtually placed objects in a meaningful way and in an immersive way. For that, you need the boundaries of the real-world objects, as you can see on the left side here. And also, we want to have the ability to interact with the real world based on what the scenery offers us. So if there's maybe a table in the scenery, we would like to put a virtual vase on the table and not put the virtual vase on a chair, for instance. A possible solution for both of the presented problems is a semantically annotated 3D mesh of the real world, as you can see in the right side image. So if you have a mesh of all the objects, you get first the boundaries, as well as an idea of where are the objects and what kind of objects do we have. And the question we wanted to answer in our paper is it possible to get this ability to scan my environment in a 3D way using only consumer level devices like mobile phones? Our solution to the problem is a client-server architecture where the mobile device is the client and a server compensates for the missing features. In this case, the client is responsible for recording the environment in a video session, which is streamed to the server. Also, it uses local libraries like ARKit in our case to perform simultaneous localization and mapping, and therefore track the camera movement in 3D space. This data is also sent to the server continuously. And we use the rendering capabilities of the client to show the objects returned by the server. So what the server then actually does is it has three microservices. One is depth estimation, which produces a depth map from an RGB input. The other one is instance segmentation based on mask scoring RCNN, which performs 2D instance segmentation based on the RGB stream from the client. And our third microservice is 3D reconstruction, which uses the estimated depth map to project both the RGB as well as the instance segmentation map into the 3D space and merge on fuse or merge continuous frames or from frames from different positions. Our microservices are based on state-of-the-art models used for, in this case, for depth estimation. We compared here 5 different state-of-the-art models, and we decided to go for the model based on Hu et al. From the year 2019. And this is mainly because they still provide reasonably high results while being quite fast with the processing, which in our case, you will see in a later example, is beneficial for the user experience. We also did the same for our instance segmentation, where we decided to use mask scoring RCNN, which is also the state of the art in 2D instance segmentation for our module. And here the main factor was just the better performance with the still reasonable around 8.6 frames per second speed. Okay, I want to show you a little video of the system in action. And this is me starting a recording. On the server side, you have the continuous estimation of depth map. Just remember, this device does not have a depth camera. And this is what the client sees. So you have the objects annotated and the corresponding meshes, as well as the full mesh of the scenery. The server then also has a reconstruction of the whole scenery in 3D, as well as the reconstruction with semantic labels of the objects inside the scenery. So can I pause this now? We evaluated our 3D reconstruction based on a 7 scenes dataset. You can see an example on the right side here, where we compare a 3D reconstruction based on a 3D sensor, in this case Kinect sensor, with a 3D reconstruction based on our depth estimation module. And we also found that at a voxel size of around 4 centimeters, we get the best ratio of error to speed. Also, we were concerned that maybe there's too much overhead between our services, our microservices on the server side. So we did some advanced performance measurements. So, and then on the bottom, you can see that the processing takes up most of the time of our services. Next big thing is uploading and downloading, which comes down to uploading and saving images from the disk to the RAM, which we could also mitigate in future releases. Okay, so to conclude my talk, we showed you a proof of concept for creating a client-server architecture that is capable of enhancing the already existing AR capabilities of mobile devices, nowadays mobile devices. The network design is modular in the sense that we have exchangeable microservices which run separately from each other and can be extended and replaced easily. Also, we showed you a demo app using a live display of the results of this server. For future, we would like to improve our microservices, starting with depth estimation, where we at the moment only are incorporating individual frames, where it would be good to also look at the past of the predictions to have a more continuous estimation of depth. Also, we want to move as many services as possible to the client to reduce the network load and get an even quicker response. And we want to implement multi-client support since we're already using a server model which is all set for collaboration. Thank you very much for the attention.